Hi everyone, I see you've made it past the initial video on how to navigate the workspace and the next card on the pre-assessments. So if you have not watched that navigation video or done the pre-assessments, please stop this and go back and do those. Otherwise, welcome to Math 10C and let's get started. So, Unit 1, Algebra and Number, Section 1, Factors and Products. This is Chapter 3 in your textbook. So there's a couple of curriculum outcomes that I want you to be aware of. You will develop algebraic reasoning and number sense by demonstrating an understanding of factors of whole numbers, by determining prime factors, greatest common factor, and least common multiples. You will demonstrate an understanding of the multiplication of polynomial expressions, limited to monomials, binomials, and trinomials. And we're going to do that concretely, pictorially, with algebra tiles, and symbolically with just algebra letters. Okay, and lastly, you're going to demonstrate an understanding of common factors and trinomial factoring, again, concretely, pictorially, and symbolically. So here is a checklist of the requirements for this section. You should have already done the pre-assessment, so go ahead and check that one off. Okay, there's 7 parts, so 7 different videos to this chapter. Okay, and then at the end of those 7 videos, or each of those 7 videos, there'll be a practice set of questions for you to work on. All the answers to those are in the back of your textbook, so please feel free to check your work as you go. Okay, after you're done the Part 7 video, there will be a chapter formative assessment. So just an assignment for you to do. Okay, after you finish that one, there'll be a curriculum review, so kind of a last assignment that counts for marks. And then, of course, you will have a quiz, okay, called the summative assessment on just Chapter 3. All right, so let's get started. Part 1, Factors and Multiples of Whole Numbers. Okay, so when a factor has exactly 2 divisors, one in itself, the factor is called a prime factor. For example, the factors of 12. So all the things that divide nicely into 12, okay, are 1, 2, 3, 4, 6, and 12. Okay, and they usually go in pairs. 1 times 12 is 12, 2 times 6 is 12, and 3 times 4 is 12. Okay, awesome. Now, the thing is, though, 6 is divisible. 6 is 2 times 3. 4 is 2 times 2. Okay, those ones are not prime factors. Okay, 12, of course, is not a prime factor. Okay, the prime factors of 12 are 2 and 3. They're the only factors that can't go any smaller. 1 is not considered a prime factor. Okay, to determine the prime factorization of 12, we write 12 as a product of its prime factors. So 12 equals 2 times 2 times 3. Okay, they're all prime. Okay, now of course 2 times 2, we can simplify that as 2 squared. So 12 equals 2 squared times 3. Okay, now this course we're going to be using the symbol x an awful lot as a variable. So in order for us to not confuse the variable x and the multiplication sign, we're going to use dots for multiplying. Okay, so 2 dot 2 dot 3. So 2 times 2 times 3. Okay, that shouldn't be anything new for you guys. So 12 equals 2 squared times 3. Perfect. So the first 10 prime numbers, okay, 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. Not that you'll ever have to list them, but something that you should notice from this list, okay, the only even prime number is 2. Everything else is odd. Now, we do skip some of them. Like you can see here, we've skipped 9. We've skipped 15. Well, 9 is 3 times 3, so that 9 isn't prime. Okay, 15 is 5 times 3, so that's not prime. Okay, etc., etc. So, okay, natural numbers greater than 1 that are not prime. Okay, so the opposite of prime is called composite. Okay, and when you think of what the word composite means, it's composed of. Okay, so composite numbers are composed of 2 or more prime numbers. Okay, so example 1, determining the prime factors of a whole number. Okay, so one of the easiest ways to do this is just with what's called a factor tree. So what we do, take this big number, and we notice right away that it ends in an even number. Well, that means it's divisible by 2. Okay, so we go 2, so 2646 divided by 2, and that is 1323. Okay, well, that one's not going to be divisible by 2 anymore, but we can see, okay, well, let's try 3, and of course that one works. So it's 441. Okay, 441 is also divisible by 3. Okay, and that works out to 147. 147 is divisible by 3. Okay, so that works out to 49. 49 is divisible by 7, and 49 is 7 times 7. Okay, and we just get smaller and smaller until these numbers work out to prime numbers. Well, remember, 2 is a prime number, 3 is a prime number, and 7 is a prime number. So 2,646 is 2 times 1, 2, 3 threes, so 3 cubed times 7 squared. Okay, so that is the prime factorization of 2,646. Okay, for 2 or more natural numbers, we can determine their greatest common factor. Okay, recall that the greatest common factors, or GCF, of 2 or more numbers is the greatest factor that all the numbers have in common. So the biggest number, another way of saying this, the GCF is the largest or biggest number that divides evenly into all the numbers of the question. Okay, for small numbers with not many factors, we can just think and work our way through it. It's not that big of a deal. For example, numbers like 20 and 30. Okay, we can run through the factors in our heads. Okay, 20 is, I don't know, 2, 4, 5, 10, 20. Okay, for 30, 1, 2, 3, 5, 6, 10, 15, and then 30. Okay, whatever, that's really not that important. Okay, but when we do that, we go through those numbers in our head and we reason that 10 is the biggest number that divides nicely into both. So 10 is the GCF of 20 and 30. Okay, well, that's all swell and fine, but you know what's coming. However, with large numbers, with lots of factors, this can be difficult. Prime factorization is a helpful tool when finding the GCF. Okay, so what we're going to do is we're going to take these big numbers and we're going to find the prime factorization, and we can use factor trees or just whatever. Okay, I kind of like factor trees. They're very visual, but you don't have to use them. Anyways, okay, so for 126, and let's just write over here. So 126, that's even, so that's divisible by 2. Okay, that's 2 and 63. And to get the 63, we just go 126 divided by 2. Okay, so then 63 is 7 times 9. Okay, and then 9, of course, is 3 times 3. So the prime factorization here is 2 times 3 times 3 times 7. Or, of course, 2 times 3 squared times 7. Okay, we do the same thing for 144. Okay, 144 is, well, I know that's 12 times 12. Hopefully you do too, but if you don't, 144 is divisible by 2. Okay, so you can start that way, but if you start with like the biggest numbers you can, then it's just better. Okay, so 12, of course, is 4 times 3, 4 times 3 again, and of course the 4 is 2 times 2, and then 3 just hops down. 2 times 2 times 3. Okay, so we have 1, 2, 3, 4 2s. So 1, 2, 3, 4, and 2 3s. 1 and 2. So another way of saying that is 2 to the 4th times 3 squared. Okay, so now that we have the prime factors of all of these, okay, now the GCF is simply the prime factors that are present in both lists. Okay? And then not just present, but the lowest exponent. Okay, so if we have a look, so 2 is in both lists. Okay, so 2. So we write that down. Okay, now look, the lowest exponent, so that's 2 to the 1, that's 2 to the 4. So the lowest exponent is just 2. Awesome. Okay, we have 3 in both lists. The lowest exponent in both lists, is a squared because it's squared in both lists. Okay, now look, 7 is not in both lists. 7 is only in the 126, so 7 doesn't factor in. So this is our GCF. Okay, so let's see, 2 times 3 squared. Okay, 3 squared is 9, 2 times 9 is 18. So our GCF here is 18. Basically, if you take this, 126 divided by 18, 144 divided by 18, they both divide nicely. So that is the biggest number that divides nicely into both of those. Okay, so let's recap GCF. Okay, so the primes or prime numbers, if you prefer, prime numbers that are present in both lists and the lowest exponent. So have to be in both lists, lowest exponent, done. Awesome. Okay. To generate multiples of a number, we simply multiply the number by the natural numbers, so 1, 2, 3, 4, 5, so on. Okay, so here's some multiples of 26. So 26 times 1 is 26, 26 times 2 is 52, 26 times 3 is 78, 26 times 4 is 104. So all of these numbers are called multiples of 26. Okay, so for 2 or more natural numbers, again, we can find their least common multiple, or LCM. The least common multiple of 2 or more numbers is the least number that is divisible by each number. Okay, another way of saying this, okay, the LCM is the smallest number that divides evenly by all the numbers in the question. Okay, so the LCM is always going to be bigger than the numbers in the question. Okay, we can determine the least common multiple of 4 and 6 by combining identical copies of each smaller chain to create 2 chains of equal length. So if we look at this, so there's 4. Okay, so if we take multiples of 4, so here's the first multiple, second multiple, third multiple, or third copy. Okay, so we get 4, 4, 4. So this is a chain 12 units long. Okay, and then if we do the same thing with 6, so the first copy, 6 and 6 is 12. Okay, so the lowest common multiple between 4 and 6 is 12. Okay, so the shortest chain possible is 12 cubes long. Okay, so we say the least common multiple of 4 and 6 is 12. Okay, awesome. But once again, with large numbers, with lots of factors, this can be really difficult and really time consuming. Okay, prime factorization can be helpful for this as well. Okay, so determine the least common multiple of 28, 42, and 63. Okay, and just for the fun of this, let's just kind of number crunch this. So let's figure out all the multiples of 28. Okay, so I'm going to write up here because I'm going to do the LCM or the prime factorization lower. So 28, then 56, 84, 112. You know where I'm getting these numbers from, right? So 28 times 1, 28 times 2, 28 times 3, 28 times 4. Okay, 112, 140, 168, 196, 224, and 252. Okay, hopefully that's high enough. Okay, then we go 42. Well, I know it's high enough, but you wouldn't know that if you were doing it this way. So I just go for a while and see if it's, okay, 168, 210, 252, and 294. Okay, and then lastly we get 63, 126, 189, 252. Oh, wait, look at that. Okay, 315. Look, guys, 252 is the first number that occurs in all 3 lists. Okay, look, 126 occurred in the bottom 2 lists, but it didn't occur in the top one, so that one doesn't work. Okay, 252 is the first one that appears in all three. So you can do it that way. Like, that's not that big a deal, but it's just a little bit of a pain. Okay, so how we do this with prime factorization? Okay, we just take 28. Okay, well, that's 4 and 7. So that's 2 and 2 and 7. Okay, so 28 equals 2 times 2 times 7, or 2 squared times 7. Okay, 42, on the other hand, 42, okay, so that's 6 times 7, which is 2 times 3 times 7. So 42 equals 2 times 3 times 7. Okay, there's no simplify for that one, because there's... Okay, and then 63, okay, well, that's 9 times 7, so that's 3 times 3 times 7. Okay, so 63 is 3 times 3 times 7, which of course is 3 squared times 7. Now, the LCM, just like the GCF, okay, the LCM is the highest exponent, the highest this time, right? The LCD was, or the GCF, pardon me. GCF was the lowest exponent. The LCM is the highest exponent on every number in all the lists. Okay, so if we have a look, so we've got 2, 2, 7, 2, 3, 7, 3, 3, and 7. Those are our numbers. Okay, so we have a 2. Okay, 2's there. We only have to write it once for now. Okay, so 2's there. 3 is present in the lists. Okay, and 7 is present in the lists. Okay, so those are all the numbers that are present, 2, 3, and 7. And now we need the highest exponent. So if we have a look, 2 has a highest exponent of 2, so 2 squared. Okay, 3, the highest exponent of the 3, is also a squared. Okay, and then the 7 is just 7 to the 1, 7 to the 1, so that's as good as we can get. So if we multiply this, so 2 squared is 4, 3 squared is 9, and times 7, if we multiply all those, we get 252. Well, look, we already knew that 252 is the answer because we did it the long way up here. Okay, so just to recap, the LCM is the highest exponent on every single number in the lists. Okay, it doesn't matter if the number only appears in one list, we still have to include it. Okay, we just have to make sure that it's the highest exponent on every number that's present. Okay, awesome. So there is that one. Okay, example 4. So solving problems that involve a GCF for an LCM. Okay, so A, what is the side length of the smallest square that could be tiled with rectangles that measure 8 inches by 36 inches? Assume the rectangles can't be cut. Okay, so we need some kind of a square. And I want to tile this, and I'm tiling with tiles that are 36 inches long. It's a terrible drawing. 36 inches long by 8 inches wide. Okay, awesome. So really, this is a lowest common multiple kind of thing, an LCM. Okay, now the reason why it's one of those is because I want numbers that are bigger that go evenly into both of those. Okay, so remember, I want a square. So I want to make sure that this side length ends up the same as that side length. Okay, so we can do this with multiples, or we can do this with prime factorization. I'm going to choose prime factorization. So look, 8 is 2 times 4, which is 2 times 2 times 2. So 8 equals 2 cubed. Okay, awesome. 36, okay, is 6 times 6, which is 2 times 3 2 times 3 again. So 36 is 2 squared times 3 squared. Okay, awesome. Now remember, to figure out the LCM, lowest common multiple, I need all the numbers that are in the list. So there's a 2 and a 3. 2 and a 3. Okay, and then I need the highest exponents of them. So the highest exponent of the 2, so I've got a 2 cubed and a 2 squared. The high exponent is 2 cubed. Okay, and the highest exponent on the 3 is a 3 squared. So I've got a 3 squared times, a 2 cubed times 3 squared. So that's going to be 8 times 9, so that's 72. So 72 is the lowest common multiple of 8 and 36. So that means that I can tile an area of 72 inches by 72, and let's just draw that on here. 72, so that's 2 36s. Okay, and then that's 8 inches each, so then I can get 72 divided by 8, so I can get 9 tiles down, and that would make a square 72 by 72. Okay, so sketch the square and the rectangles. So I think I've already drawn it too big to, so this would be 1, 2, 3, 4, 5, 6. Okay, well, I didn't do that right. 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. So that doesn't look like a square anymore because I've drawn it so horribly. But again, it's 9 tiles down makes 72 inches, and 2 tiles across makes 72 inches. So we're good to go. Okay. Now B. What is the side length of the largest square that could be used to tile a rectangle that measures 8 by 36? Okay. Assume the squares can't be cut. So now we're going to try and take one of these tiles from the first question, 8 by 36. So what's the smallest square that I can use to tile that? Okay, so we have 8 by 36, and I want these tiny little squares to tile that part. Okay, now this, of course, is a GCF question. So I want the greatest common factor of 8 and 36. So what's the smallest number that divides nicely into both of those? These numbers are small enough that you can probably do that in your head. Okay, 8 divides by 1, 2, 4, and 8. 36 divides by 1, 2, 3, 4, yep. 4, not 5, 6 though, 6 squared. Okay, and then 4 times 9 was 36. So this is the pairs, right? So 4 times 9, 3 times 12 made 36. 2 times 18 makes 36, and 1 times 36 makes 36. So if you have a look, 8 was only 1, 2, 4, and 8. So look, 4 is the greatest common factor, so the biggest square that can go into all of these is 4 by 4. Now, of course, 4 is half of 8, so I kind of draw that wrong again. Okay. Be better if these were to scale, but they're not. You guys get the idea. Oh, that was not a straight line at all. Okay, so 4 by 4, and then of course 4. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Oh, one more. 9. There we go. So we have 9 by 4 is 36, and 2 by 4 is 8. So we can make 4 by 4 squares. I'll tell you what, just for the fun of it, let's do that with the prime factorization just because we can. So remember, 8 is 2 times 2 times 2, which is 2 cubed. Okay, and 36, let's see, well, 36, 6, and 6. So remember that, well, it's the same as before, so that's 2 squared times 3 squared. Okay, now remember, for the GCF, we take the numbers that are in both lists. Okay, so 2 and 3. Okay, so the numbers that are, common to both, numbers that are the same in both lists. So that's just the 2. Okay, they're the same in both lists, and we take the smallest exponent of them. So 2 cubed, 2 squared, the smallest exponent is that. So the GCF is 2 squared, which of course is 4, which is what we figured out. So you can do it both ways, and it's not that bad once you get the hang of it. So guys, that's the end of this part. I would like you to practice. This is section 3.1 in your textbook, starting on page 140. So there's a bunch of questions there. Remember, you can check your answers in the back. Make sure you show your teacher when you're done so that they can send you on to the next one. But there you have it. We'll see you next section.